Okay, so today we will see some of what is known as real analysis in mathematics. We will not do real analysis, we will not even touch the core of it or even get to see it, but we will somehow have a feeling about what it is. Analysis is a field of mathematics, and well, you could say analysis is just calculus done abstractly. That's a very loose way of saying it. But analysis deals with systems in a very foundational manner, right? In a very rigorous way. So analysis is not calculus, but it is about how you come up with the operations and calculus itself. So when we do real analysis, we start from the very scratch. We start from what are real numbers, what are numbers themselves, what are the operations they do, and then we build towards what you can do with those things. Then we build towards functions, then we build towards limits of functions, and all sorts of cool things that you can do. But instead of a calculus course, which just immediately takes you there, analysis is very careful about how it approaches things. So you have to do things from the ground up. We will do some of that today. We will see an axiomatic systemization of the real number system. Most of you have seen the real numbers in one way or another, but I would not think that you have seen an axiomatization of the real number system. And this is important both to understand, to have a better understanding of real numbers, but it's also important to have a thinking about how to approach the concept of real numbers. And this thinking is developed by seeing the axioms and working with the axioms themselves. So that's what we will do. The readings are 13.1 to, sorry, this is not 13.1, this is 3.1. Chapter 1, 3.1 till 3.7 of Apostle. Okay. So as an introduction, real numbers are familiar to you. You know the positives, the positive integers. You know what integers are. You know their properties. You know what a rational number is. Rational numbers. You know what an irrational number is. Root 2 is irrational. We just did a very nice proof of that last week, and other irrational stuff. The difficulty in mathematics is when you have a system of numbers or a system itself, and you have to figure out another way to do some other things which are very similar to what we did, but do not agree with some of the foundational axioms. One of those is how to go from irrational numbers to rational numbers. Another thing to compare it would be how to go from complex numbers from real numbers. That was a whole different deal. There was debate on if complex numbers are actually better, or how do they compare to real numbers. But as we realize, real numbers are actually a subset of complex numbers, right? So that's how those are the sort of moments of antagonism where we're confused what to do. Okay, so the book would start from giving the axioms. Some important things about what the book does is that the author says from the beginning, the point of view they adopt is non-constructive. So if you remember when I talked to you about intuitionism and constructivism, they have a different way to approach analysis. And I also mentioned a book. There's Anderson's non-traditional, sorry, I forgot the name. Non-conventional analysis or something like that. But
Non-standard analysis.
Non-standard analysis, yes, thank you. Which does analysis in a constructive way. So the author here does not do that approach. So they say that we should start rather far out in the process, taking the real numbers themselves as undefined objects. So like when we were doing axiomatic set theory, I assumed that sets are something. I already told you that, sets are there. We're not going to, like, the only way we're going to define sets is through the axioms, right? So that's what they're doing here as well. So we shall assume there exists a set R of objects called real numbers, which satisfy the 10 axioms, which we will just say, and all the properties of the real numbers can be deduced from the axiomatic system. Okay, some notational stuff. Whenever we bring any lowercase letters, they will be arbitrary real numbers, unless we mention anything otherwise. The axioms are of different kinds, or different groups. There are field axioms, there's the order axioms, and the least upper bound axiom, which is also known as the axiom of continuity, or the completeness axiom. We will see more on that. Another note before we continue is that if you had taken a look at the week 0 notes, which have been posted in the GitHub repo, a minute. The part of the notes have a list of definitions that are not something we covered in the lectures, but they are very important to have in mind. Some of those definitions are going to be used here. More importantly, about bounds, what an upper bound is, what a lower bound is, what is a maximum, minimum, supremum, least upper bound. Those kind of terminologies would be used. So if you do not figure out, ask or refer to this. Okay, so we will start with the field axioms. So along with what we said that the real numbers are something undefined, and they're just a set with some objects in there that we call real numbers. We also assume that there are some operations known as addition and multiplication, which we can form on these real numbers, right? And how we denote them is by x plus y, which means the sum of x and y, and product by x, y, or x dot y, right? There's nothing that is new here, except the fact that the sum and the product are uniquely determined by the pair of real numbers that we choose. This is part of a general idea in defining operations on objects known as binary operations. So what binary operations do is that they take a Cartesian product. So they take R cross R. So R cross R means you're taking a tuple of two elements. So you have A, B, or X, Y from R cross R. And what you're doing is you're operating on that tuple to get something else, another real number, right? So to emphasize on the uniquely determined part is that this function is always going to be, the binary operation that I said, always is going to take a tuple of two elements and is going to give you exactly a specific another product or sum. Okay. So along with these operations, we define the axioms, and the axioms are not going to be alien to you. Most of them, some of them are going to be alien to you, but these are the axioms. The first axiom is the commutative law. So the commutative law says if you have two real numbers x and y, if we add them, which is x plus y, then that is going to be equal to y plus x. Similarly, if we have the product operation, then x times y is equal to y times x. This is the commutative property over real numbers. The associative property is similar, something you have seen before. It says if you have three real numbers and you're operating on them separately, so you have x plus the real number formed by the addition of y plus z, and that is going to be equal to the addition of the real number formed by x plus y, then added with z, right? So you can see the associative law says you can operate on real numbers in groups and it's still going to be valid. Same for products. The distributive law says you can have the operation distributed across other operations. So x times y plus z means you have the operation of multiplication distributed over this sum, which is, of course, doing another operation. Those are the first three laws, something you have seen since grade 4 or 5. Axiom 4 says there is an existence of identity elements. So identity elements are basically special kind of real numbers, so special kind of things in a set. So what the axiom says is that there exist two distinct real numbers which we denote by 0 and 1, such that for every real number x, we have x plus 0 equals to x, and y times x equals to x. So here's a shift in thinking that you have to do, which is that x plus 0 equals to x is not due to 0's property. We do not assume any property from 0. 0 is just another real number like everything else. What makes 0 special is that it is a specific element which, when added with any other real number, gives you that real number. Do not get fixated on the symbol of 0 itself. We can use anything else and it can act as the same identity element like 0 is doing. And in more abstract mathematical areas, you will see that happening all the time. So 0 and 1 are two distinct real numbers which when added or multiplied with any real number give the same number back. That's the existence of identity elements. Then the fifth axiom is the existence of negatives, or what we might call the existence of inverses. So what it says is that for every real number x, there is a real number y, such that x plus y is equal to 0. Right? So for every real number that you pick up from the set of real numbers, there has to be another real number which, when you add them, will give you the 0. Again, do not get fixated on 0. What it must give you is the identity element. So this is, again, the shift in thinking that I'm asking. It's not that x plus minus x has to be 0, and that's important. What's important is that the definition of an inverse number, or the definition of the negatives, is that when you add them, you get a special kind of thing which has this property of being the identity. Do not fixate on the 0. Because we're working on real numbers, this is fine. You can think of 0 because 0 is used everywhere. But 0 is not a special. You can have a lot of things work like that. Axiom 6 says there is an existence of reciprocals. So reciprocals are also inverses, but there are inverses in the operation of multiplication. So for every non-zero real number that you choose, or non-trivial real number, another way to think about, there is a real number y such that when you do the operation of multiplication on x, you get the identity element 1. So think of the identity elements with respect to their operations. When you're talking about the operation of addition, you're talking about the identity element 0. And when you're talking about the operation of multiplication, you're talking about the identity element 1. Right? So again, the existence of negatives is the inverse operation happening on the elements, the real numbers, to get 0, because we're talking about addition. And when you're talking about inverse operation in multiplication, we're going to talk about reciprocals, and the identity element would be 1. Okay? So from these 6 axioms, you can do all elementary operations in real numbers, or elementary algebra, as they say. And from these operations, you can define certain important theorems that are very foundational, let's say. So the theorem 1.1 talks about the cancellation law for addition. What it says is that if a plus b is equal to a plus c, then b has to be equal to c. In particular, this shows that the number 0 of axiom 4 is actually unique. There is only one such 0 for which, when you add that number with any other real number, you're going to get x. This might sound like really obvious. It is not. It is something that you've seen since grade 4 or 5 or much younger, which is fine. But the change in thinking is that it is not about crossing things out on both sides. What you're doing here is you should be, again, whenever I'm talking about things like these equations, you should know that I'm talking about the operation. And I'm mentioning the operation because that's how I think in my mind. I am thinking about an operation taking 2 things and giving me 1 thing. And you can say, okay, that's a trivial thing. I mean, that's actually what's happening, but this is just a plus b. But no, when you do that kind of shift in thinking, it helps you understand. So again, when you're talking about a plus b, this is an operation done from 2 real numbers to give 1 real number, which is a plus b. And if that is equal to a plus c, then what we can say is that as the operation on both the sides, it has 1 common real number to it, the other 2 have to be equal. Because I told you, when I told you about the binary operation, is that it takes things from a Cartesian product, a tuple of 2 elements, and it gives you a precisely unique real number or anything else. So what this means is that if you have the first components of the tuple equal, then the other components, if the first components are equal and the product itself is equal, then the other 2 elements have to be equal, because I told you the operation does uniquely. So the operation is always going to give me a unique product for every distinct 2 real numbers I give it as input, right? So that's how you should think about it. Do not think about this in terms of canceling things out. Think about it in terms of operations. Theorem 1.2, which says the possibility of subtraction. So subtraction as a possibility happens from the previous theorem actually, but let's see. It's more corollary or deduction from the axiom of 5 of negatives. So what this says is that given a and b, there is exactly 1 x such that a plus x is equal to b. This x is denoted by b minus a. In particular, 0 minus a is simply written as minus a and is called the negative of a. Again, like before, do not think of transposition or substitution or any of those things. X is not, you do not arrive at x by just pulling a into this side. That is technically true, but that's not what we're dealing with here. Again, think about it in terms of operations. So what this possibility or this theorem means is that if you take two real numbers, there is exactly one real number out there such that you can add x to one of those real numbers to get another. So a plus x equals to b means there is exactly one x which will make this operation possible. And that x is b minus a. Okay. And when your b is 0, so when you're considering the x such that a plus x is equal to 0, then you're going to get 0 minus a. And 0 minus a, we denote it just simply with minus a. And minus a is the negative of a from the axiom of the negatives, right? So that's subtraction. Theorem 1.3 says that b minus a is the same as b plus minus a. Again, to remind you, do not fall into the temptation of saying this is just plus a bracket minus a, which means, you know, in middle school or in whenever you learned negative numbers, you were told that when you do this plus times the minus, you get minus. That is like black magic, something you were told and you were taught to remember, and there was no foundation to it. Similar things happen in university too. The example is determinants. The Kramer's rule in determinant is actually black magic. A very hot take. So when you think about b minus a and b plus minus a, always think about them in terms of operations. So b minus a is a separate thing when you're operating the subtraction onto two real numbers, and b plus minus a is the operation of addition on b and the negative of a, and the negative of a is the inverse of a, right? Which goes back to the axiom of negatives and which goes back to the axiom of identity elements, right? Think of it like that. Theorem 1.4 says that minus negative of negative a is equal to a. Again, do not fall back to the black magic thinking, which is minus times minus is plus. That's not what we're doing here. What we're saying is that if you have a negative a, what is negative a? Negative a is simply the number which when added with a will give you the identity element for addition, which is 0. And when you take the negative of that, when you take the negative of negative a, you're going to get the same number back, because the only number which when added with negative a, which will give you 0, is a. So here, when you're considering the negative of negative a, it's a. So you can see there's a mutual correspondence there. A is the negative of the negative a, and negative a is the negative of a. That's a bit mouthful, but think about it. That's theorem 1.4. Theorem 1.5 says that a times b minus c is the same as ab minus ac. So you can see this is just laying down the properties of subtraction. So a times b minus c, you can say that this is just distributive property of multiplication over addition over subtraction, right? So ab minus ac. Then you have this neutral element 0, which says that whenever you multiply 0 with any real number, it gives you 0, right? So another thing to note is that 1 is the identity element in the operation of multiplication. Whenever you're thinking about identity element, think about the fact that it takes something and it gives you the same thing back. It's like a function. It takes something and it gives you the same thing back. And it's in general, in all of mathematics, we call this the identity map. It's a function taking something and giving you the same thing back. So in the operation of addition, in the operation of multiplication, 1 is that identity. But there's also another special kind of thing that happens in multiplication, is that there's this neutral element. What the neutral element has as a property is that whenever you put anything into it, it gives you the neutral element back. So 0 times a, or a times 0, always gives you 0 for any a you have, right? And again, this is not particularly interesting about 0, it's more interesting about the operation and the identity element itself, so the neutral element itself. We will go through a few more theorems, and then I will stop, and then I will see if you have any questions. Theorem 1.7 is about cancellation law for multiplication. Again, if you have AB equals to AC, and A is a non-trivial or non-zero real number, then B is equal to C. In particular, this shows that the number 1 of axiom 4 is unique. That is, the identity element over the operation of multiplication is unique. So again, when you're considering AB equals to AC, do not fall to the temptation of just cancelling A from both sides. That is black magic. What we were doing is, if we have the operation of multiplication, which takes two things, AB, and it gives you A times B, and then again the operation takes AC, and it gives you A times C. And if we say that A times B and A times C are equal, then B and C have to be equal. Because again, think about it in terms of how I explained in the addition operation. You have the tuple, you have A comma B, and you have A comma C. And if the product of those two tuples, when done, the multiplication operation gives you the same thing, then the other two components in the tuple have to be equal. That is, B have to be equal to C, right? Because the operation happens uniquely. So in this case, it is not anything special in multiplication that makes things happen, because as I told you, the underlying operation is exactly the same. They are both binary operations. So it is not that, if you have A plus B equals to A plus C, you can cancel, and A times B, A times C, because this multiplication you can somehow cancel. That's not what we're doing. So that's the cancellation law for multiplication, very similar to 1.1. Then we have theorem 1.8, which is the possibility of division, which says given A and B with A being non-zero, there is exactly one x such that A times x is equal to B. So this is very similar to possibility of subtraction. So I don't know about you, but when I was in grade 2 and I was introduced to division, I always thought, I think I still had that kind of thinking later when I was doing calculus, but the thinking was that division and subtraction are analogous, as addition and multiplication are analogous. And I did this very not stupid, but like I had this childish thinking, which is that if you take the addition symbol and you kind of tilt it, you get the multiplication symbol. So that's how they're analogous. And when you take this symbol of bar or the hyphen in subtraction and you put things over there, you get division. So that's how I got subtraction and division similar, addition and multiplication similar. But the truth is, the way we get subtraction from the cancellation law of addition is similar to how we get division from the cancellation law of multiplication. So I was not entirely wrong, but there is this kind of a derivative. So the possibility of division stays the same. Just like we had A plus X equals to B, this time we're having the multiplication operation. So A times X is equal to B. And this X is denoted by B over A, or B divides A, right? And this is the quotient of B and A, right? So when you have the division operation happening on B and A, we get something like the quotient. And the quotient is X. Okay, do not think that you're just taking A to this side over this side and then you have B over A, yada yada, that is X. It looks similar, but that's not what's happening. We're again, think in terms of operations. So again, if we have the special case when X is equal to 1 instead of B, so B is equal to 1, then 1 over A is going to be your special reciprocal, which is A inverse, as you've always known it. That's the reciprocal, going back to axiom 6 on the existence of reciprocals. This is theorem 1.8, very similar to theorem 1.2. Theorem 1.9 till 13 are very similar to what we did, so I'll very quickly go through them. If you have A as a non-zero, then B over A is the same thing as saying B times A inverse. Something that you have seen before, but this is what you're saying. If A is a non-zero integer again, then the inverse or the reciprocal of the reciprocal of A is equal to A. Think of it the same way I gave you the negation of A, or the negative of the negative of A, right? So if you think of it like that, the inverse of the inverse of A is equal to A. So A and inverse A and A to the minus 1 have this correspondence. A is the reciprocal of A, and the reciprocal of A is the reciprocal of A. A minus 1 is the reciprocal of A. Right? So there's this correspondence. If AB is equal to 0, then either A is equal to 0 or B is equal to 0. Again, sounds very obvious, but that is not so. Think of AB as the operation of multiplication applied on them to give you the identity element for addition. And again, I'm almost halfway through explaining the proof of each of these things, but when you look at the proof, you'll see there's some work there. Theorem 1.12 says that if you take the negative of A times B, you're going to get the negative of AB, and you're going to get negative of A times the negative of B, and both of them are equal to AB. So you see, do not fall to the temptation of saying just remove the brackets. This is negative of A times B, and this is negative of A times B, right? So you're multiplying different things. And here you have negative of A times negative of B, which is equal to A times B. Similarly, for division, you have A over B plus C over D. A over B plus C over D is going to give you AD plus BC over BD, assuming that B is non-zero and D is non-zero as well. If you multiply two quotients, A over B times C over D, then you're going to get AC over BD, assuming B and D are non-zero. If you do the same thing, you can get a bit differently. You have A over B. I think there's some typo here. Yeah, A over B times C over D, A over B over C over D, and that is the same thing as saying AD over BC, assuming BC and D are non-zero. So you can see these are your axioms, theorems, 15 theorems that I quickly ran through you. They do not give the proof for all of them. They give the proof for the first 4 of them. The others, you are very much encouraged to find out and write them. Writing the proofs is going to develop the kind of thinking on how to compare the axioms to all these things happening here. And it will also train your muscle of not falling into the temptation of canceling things, or just taking things over, or minus times minus equals to plus, that kind of thinking. It will help you reduce that if you do the proofs. So yeah, those are the theorems. Any questions before I move on? Questions, comments, anything? None? Okay, great. Then I'll ask something. So when we're considering the let's say theorem 1.14, how would you go about proving theorem 1.14? It's just A over B times C over D. How do you prove it? Again, when I say prove it, you have to use either the theorems before it, or you have to use the axioms directly. So yeah, any thoughts?
Could you rewrite them as inverses and then use a commutative law for multiplication?
And how would you do that?
Well, you have A over B, so you replace that by A times B inverse. And then you have C over D, and you also replace that by C times D inverse. And using the commutative law of multiplication, you do A times C times B minus 1, D minus 1. And you rewrite those as, again, a fraction, and you end up with AC over BD. So long as B is not equal to 0 and B is not equal to 0.
Correct.
Okay.
But you forgot the main thing, when you're doing B inverse times D inverse, you have to write BD inverse. It's not 1 over A times,
Oh,
it is 1,
okay.
right, you have to, right, you have to say that.
You have to prove that first then.
Yes.
Okay.
So you have to do that because we haven't yet done that. But B inverse times D inverse would be BD whole inverse. And we know that, again, BD inverse is not, it is 1 over B times 1 over D, but it is a thing on its own. It's a number, right? BD inverse. So you have to treat it like that. Similarly, AC is a number. So AC times BD inverse is the same thing as A times B inverse, which is AC over BD. So yeah, that's good.
I'm sorry, I think I missed the part where so I did understand, I followed till like A, B inverse plus C, D inverse. But what did we apply to it to get the form on the right side? I do understand the part where you're like saying B, D inverse is
We apply the
so
commutative property, right?
okay.
Yes.
Okay.
So using commutative property, A times B inverse times C times D inverse is the same thing as AC times B times D inverse, right?
Okay. And when you
Yes.
say we should consider BD inverse as a number on its own rather than 1 over BD, it's just this is the language that will make our work more rigorous, basically.
Yeah.
Is that like the purpose for it? Okay.
So the
Rather than
purpose
being
is,
able to, yeah. Rather than being able to just translate other numbers onto it, we just think of them as unique and then
oh, you cut out. Yeah, can't really hear you. Yes.
check. Yeah,
Yes.
it's much. Yeah.
Yeah, what were you saying?
I was just saying so when we consider these as unique and we consider the operations themselves, this is all like making these building blocks and thinking about these operations as unique in themselves, rather than applying our intuitive, what's it called? Mm, elementary mathematics that we've learned. It helps us build a more robust structure, I guess,
Yes,
in the proof.
it is basically, do not say anything that you're not entirely
Yeah.
sure about. That's the idea. You cannot use a symbol, you cannot move anything around that you're not sure
Yeah,
what's
yeah, yeah.
happening.
That's why, like, if they give us BD inverse, then it's BD inverse until like we prove otherwise.
Yes, yes.
Okay.
So this kind of thinking helps you both in understanding the underlying framework on what's happening, and it helps you talk about things in a much more easier way. Because as a grade 4 student or grade 3 student, when you would be asked why minus times minus is plus, what is happening there, you can't explain what's happening there.
That's literally magic, yeah.
It is magic. The thing is, you don't really grow out of the magic in university either. That's what's one of the things I realized. To determine the Kramer's rule is
It's actually I might sound like I'm really stupid, but just looking at it right now, it really helped me to look at minus A times minus B. That really helped my brain like construct minus A and minus B. Like on a like when you cross these two number lines, like imagine two integer lines and they're getting crossed over, and you're imagining like a negative number and then another negative number, and then you can look at the number switch changing because it's a negative, and like the looking at the operation itself is like it's painful for our intuition because I've been forced as a child to learn that
Yeah.
it is what it is rather
Yep.
than to look at the operation and then discern why it
Yes.
is that way.
Yes. 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 So part of because analysis is one of the first ways people get introduced to abstract mathematics. This is the way to ditch those intuitions. So this is where your mathematician teacher feels happy and you feel bad.
Yeah, they mostly it was the other way around.
Yes.
The mathematics teachers used to feel bad.
Yes. Okay. These are some of the theorems. You're welcome just to do the proofs on your own. They're not really as hard, just 2 lines most of the time. But again, be rigorous and do not use anything that you can't be very clear about. Okay, so those are the field axioms that we saw. Next, we will, as I told you, we will see the order axioms and the least upper bound axioms as well. So let's get to the order axioms. So the order axioms is about ordering, and ordering is a sort of, again, operation that you do on things, real numbers, integers, or anything, to arrange them in certain ways. So ordering, as they say, enables us to make statements about one real number being larger or smaller than another. I would go ahead and say we're not even considering the larger or smaller part. If you consider ordering as a much more abstract operation, what we're doing is we're saying, how can I talk about this number being prior or forward to a certain moment. So if I say like
sequentially, I guess.
yes, sequentially. So when you're constructing a sequence, you can randomly put down numbers a1 till an. Okay, well, it's a1 till an. It doesn't have any like ordering, so you can't say an is necessarily first, and sorry, an is like the last thing and a1 is the first thing. You can't say that. It's just n things in a set. So when you put ordering to it, you're putting a rule onto the set in how we talk about what comes first and what comes last, or what comes first and what comes second, and so on, right? So you should think about ordering like that. It's like putting a rule on how things are organized. Dictionary is a good example of ordering. Dictionary takes all the words that are available in a certain field, and it puts them in the ordering of the alphabets, or sometimes it can have
Is
different
this
orders.
excuse me cutting you off, but is
No.
this like thinking like, okay, so we come up with this ordering, and then the mathematical properties of the numbers in that ordering come as a result of this ordering, rather than thinking like those, like thinking of normal real numbers, uh, because I personally used to come from the numbers to these conclusions rather than going towards the numbers from like these sequences in my mind.
Yes, we will see that. We will see that. What happens is, so why is 3 greater than 2? Yeah, explain to me, why is 3 greater than 2? This is the question of your life.
Uh, because in the sequence of real numbers, 3 comes after 2.
Right.
I guess
What does 3 come after
that's more
2?
rigorous than me saying. Oh, that's a tough one. That's a tough can of worms to open.
Yeah, so again, I'm going
Because
to be
somebody said so, I don't know.
right, because somebody says so. Your teacher said so. That's what I was told. But so if we get a bit rigorous, what we will say is that you have the counting numbers. You have 1 till the eternity. Let's say 1 till 10. And what we did was that we have a rule of how we arrange the numbers. First, before we even arrange numbers, we have a way of how we get the numbers. So we decided to say that 1 plus 2 is equal to 3. 3 plus 1 is equal to 4. So what we decided is that there's a rule for coming up with the next number, and it is by adding the special number called 1. Right? And then we decided that there's an ordering which says if we are applying the operation of addition on each number to get the next number, and if your numbers are all positive, then the product, the sum that you will get, is always greater than the 2 numbers. Right? So 1 plus 2 being equal to 3 means that 3 is greater than 1 and 2 because of the operation of addition. When you have the operation of addition applied on 2 non-negative or non-zero real numbers, it is always going to give you something which is in ordering higher than the other 2. Right? We'll see why is that. That's a much better explanation, but it's still not rigorous. So yeah, that's the answer to the question, why is 3 greater than 2? So voila. Okay, so when we're talking about ordering, we're considering some properties of numbers. We're considering some properties of the objects, let's say. And those properties are actually these things: positiveness, and we're considering greater than and less than. So let's see. So what we do is we take a subset of the real numbers, and those are the real numbers which we call the positive numbers. Okay? And the positive numbers satisfy these 3 axioms. These are the order axioms. This is how we define what it means for a number to be positive. Axiom 7 says that if x and y are in R plus, so remember when we first decided to lay down the field axioms, as we said, we're considering some set R, and then we're considering it has some objects that we call real numbers. But what we do here is similar. We're considering R plus, which is a subset of R, and we're considering that it has objects that we call positive numbers. We do not know what things it has, what kind of properties the numbers have. That's what we're going to say here. Axiom 7 says that if x and y are in R plus, then so are x plus y and xy. Right? So this is something that I loosely said earlier, that you have the operation, the binary operation, addition and multiplication, is going to give you something which is also in the same set. Right? So x plus y and xy are in R plus. Again, remember, we do not know what R plus has in terms of properties. We just know it's a set with these things. Axiom 8 says that for every non-zero real number, either x is an r plus or minus x is an r plus. But they cannot both be true at the same time, right? So if x is an r plus, minus x cannot be an r plus. When you say, why would minus x be an r plus? R plus is the set of positive numbers, and as I have seen in my whole life, positive numbers do not have negative, like the symbol in front of them. But again, that's falling prey to things that you do not know. Why do we say that minus x is negative or x is positive?
Divya.
Yes, sir.
R plus means positive real numbers, right?
We do not know that yet.
Oh, all right. Okay, carry on.
So either x is an r plus or minus x is an r plus, but both cannot be true. So that's axiom 8. Axiom 9 says 0 is not included in r plus. Okay. So those are your 3 axioms. Now that we have this set r plus with these sort of things in it, we do not yet know if it's positive or negative. We do not know what even positiveness means. Right? We just have a set r plus with these 3 axioms. Now we define certain symbols to talk about relationships between two things. So this is one thing that I regret not doing, but when our prerequisite weeks were going on, I should have introduced you to something called equivalence relations and binary relations. I think part of it is in the notes. If you go here, I have defined what an equivalence relation is, what a binary relation is. A binary relation is what I've been talking to you until now, is the binary operation. It takes two things and it says whether something is true or false. A binary relation has to satisfy 5 things, sometimes 3 things, the other 2 are optional, let's say. It has to be reflexive, it has to be symmetric, and it has to be transitive. Those 3 things and other things have some certain meanings, and if you go through them, which I recommend doing, then you would understand what's happening in this greater than and less than equal to symbols. They are binary relations. In some ways, they're equivalence relations as well. So yeah, that's a note. Check out when you have time, or ask if you do not understand. So we can define the symbols like this. You have this symbols brackets, angular brackets, and you have a specific kind of those brackets where you have this bar underlying them. And how we define these symbols is that the first one is less than, the second one is greater than, the third one is less than or equal to, and the fourth one is greater than or equal to, right? Again, I recommend thinking about these symbols as binary relations or equivalence relations. Think of it like that. So x less than y means that y minus x is positive. Y greater than x means x is less than y. And what does x less than y mean? X less than y means y minus x is positive. X less than or equal to y means that either x is less than y or x is equal to y. Y greater than or equal to x means that x is less than or equal to y. So you can see they're interconnected. So x is greater than 0 if and only if x is positive. X is an r plus. If x is less than 0, we say that x is negative. If x is greater than or equal to 0, we say that x is non-negative. It is not negative. But it doesn't have to be positive, it can be 0, and we do not consider 0 in r plus, right? So yeah, these are the inequalities. You've probably seen them before, but this is more rigorous. So what we can do is we can take these operations and we can define some more theorems like we did before, like about 10 theorems. And these theorems are about the properties of these relations. Okay, I'll quickly go through those theorems and explain whenever needed. Theorem 1.16 says about the trichotomy law. The trichotomy law is about taking two real numbers a and b, arbitrary, and there's exactly one of the three relations that has to be true at one time. It cannot be true at the same time. So either a is less than b, or b is less than a, or a is equal to b. Those three things have to be true independently. One of those three things have to be true at one time. They cannot be true at the same time, right? 1.17 is the transitive law. Transitive law, this is why I intended to bring up the binary relations. The transitive property, if I were to quickly go through it, the transitive property says if you take three things in a set, and here r of x, y is just a relation, an operation, like x. You can think of r of x, y is actually x less than y or x greater than y. It's just an operation acting on two things. So if you take three things in the set, and you say r of xy and r of yz is true. So if these two statements, again, these are logical statements, if these statements are true at the same time because there's an AND operator, then that implies r of xz is true, right? So what this means in terms of our operations is that if a is less than b, so you can think of this like that, less than operator, a relation applying on two things, a and b, and then the less than operator applying on b and c, then a is less than c. And you should see how this is similar to when I explained to you the cancellation laws. When I talked to you about the cancellation law, I said you're taking from a tuple, and the first components of the tuple are the same. And if you're getting the same thing, or you have similar some kind of similarity, then the other two elements in the tuple have to be equal. So this is the same thing. So if a is less than b and b is less than c, then a is less than c. Right? That's the transitive property. 1.18. What 1.18 says that if a is less than b, then a plus c has to be less than b plus c. Right? Again, do not think of it in terms of adding c on the both the sides. That's not what's happening. What's happening is that a plus c as an element from operation of addition is less than b plus c because you have the same operation, same element c in both of those. So again, think of it in terms of operations. 1.19 says something similar. If a is less than b and c is greater than 0, then ac is less than bc. If a is not equal to 0, if a is non-zero, then a squared or a times a is always greater than 0. Theorem 1.21 says that 1 is greater than 0. Good luck proving that. 1.22 says that if a is less than b and c is less than 0, then ac is greater than bc. Something you should be familiar with, but would have a hard time understanding how they operate. Because again, go back to the axioms. Always go back to the axioms. What does the symbols mean? And they mean something recursive, and they're interrelated, and you'll be able to prove. 1.23 says that if a is less than b, then negative of a is greater than negative of b. In particular, fa is less than, this is not fa. This is if a is less than 0, then negative of a is greater than 0. Right? So you can see, so this is why negative of a sometimes can be in R plus. 1.24 says that if ab is greater than 0, then both a and b are positive or both are negative. If the product over multiplication is greater than 0, then A is greater than 0 and B is greater than 0, or A is less than 0 and B is less than 0. The last one says that if A is less than C and B is less than D, then A plus B is less than C plus D. This is another one of those, inequality stuff which you learn. If you have the same kind of inequality, then you can, add the left side, the right side, and still have the inequality, which is, again, black magic, but you would have to prove why that is so. And they prove some of these. They prove 16, 17, 18, 19, 20, 21. If people want, I can go through one or two of these proofs if they want to kind of understand how they're doing it, or I would just ask for any questions and move on.
Maybe just look at one, or we can just move on, I guess. Or we can just read it later as a assignment.
Well, you have to do all of those later. But let's see, if I had to pick 19. Let's see, 19. So 19 says, again, going back, if A is less than B and C is greater than 0, AC is less than BC. You have to prove that. Okay, so if A is less than B, what do we know? We know that B minus A is greater than 0. That's the definition of A is less than B. If C is greater than 0, then by axiom 7, we know that we may multiply C by B minus A, and we can obtain B minus A times C is greater than 0. So axiom 7, if you go back, has this. If x and y are in R plus, x plus y and xy are both in R plus as well. So, wait, where was I? B minus A times C is going to be in R plus. That's why it's going to be greater than 0. But B minus A times C is equal to BC minus AC. We have seen that. So BC minus AC is greater than 0. And by the definition of the less than symbol, or the less than relation, BC minus AC greater than 0 is the same thing, or equivalent to saying AC is less than BC. Okay? So yeah. Okay, any questions before I get to the last two sections? The rational numbers and a bit of geometric interpretation. We might not be able to do the geometric interpretation totally, but we will see. Any questions?
Nope.
Okay. So let's get into rational numbers and integers. So what we did was we gave 9 axioms. We haven't yet gotten to the 10th axiom. We gave 9 axioms for real numbers. Right? We showed how the real numbers work in terms of the operations. Then we showed how can we order the real numbers. We introduced this notion of positiveness, and then we have from positiveness these relations which allow us to define all kinds of cool stuff. So now what we can do is we can extend our exploration, and we can figure out how can we further partition the real numbers. Okay, that is, find subsets. So yes, there exist certain subsets of R which are distinguished because they have special properties that are not shared by all other real numbers. In this section, we will see two of those. We will see the integers and the rational numbers. So how do you talk about integers? Well, we'll see. This is where induction will come into your help. So we start with the number 1. We know that number 1 is guaranteed to exist because of the existence of the identity element. So number 1 is always there. Then the number 1 plus 1 is denoted by 2. And if we do not go into the messiness that Russell had in his proof of 1 plus 1 equals to 2, we just say that the number 1 plus 1, which is a unique number arrived at by the binary operation of addition applied on 1 with itself, you get something 1 plus 1, which we denote using notation as 2. That is shorter than what you will have to do in Russell's book, the Russell's proof. Yeah, that's 1 plus 1 denoted as 2. 2 plus 1 is denoted as 3, and so on. That is how we come up with counting numbers. It is not, let's say, it is constructive in some sense, but it is not entirely rigorous. Numbers 1, 2, 3, and so on are obtained in this way by repeated addition of 1. And all the numbers that you get like this are positive. They are called positive integers. So we don't have a specific and rigorous definition of what we mean by positive numbers, right? But we have this intuitive understanding of what's going on. So one can define positive integers in many ways, depending upon the tradition you're coming from. It will vary, but here we will do using the induction. That's what Apostle does. So we have something called an inductive set. So a set of real numbers is called an inductive set if it has the following properties. You have 1 in there, and for every set x in the set, the number of x plus 1 is also in the set. This is just stating the definition of the principle of mathematical induction, replacing the truth statements with the word set. If what we said last time in the induction is that if the proposition is true for 1 and it is true for some k of n, and if you can show that it is true for k of n plus 1, then it is true for all the numbers, all the natural numbers. What we're doing is very similar. What we're saying, if 1 is in the set, that is 1, that is the base step, and then we say if for every x that you choose from the set, if you can find x plus 1 to also be in the set, then you get if for every x that you choose in the set, if x plus 1 is also in the set, that's the second necessary requirement for it to be an inductive set. So as you can see, if you keep this running, it will generate more and more numbers as we pick more and more x's, right? R is an inductive set. R plus, which is a subset of R, is also an inductive set. So this is how we define the positive integers. We say that a real number is called a positive integer if it belongs to every inductive set. That might sound a bit weird, but that's exactly what we're doing. So real number is called a positive integer if it belongs to every inductive set. So every inductive set that satisfies these two conditions, if it has something in it, is going to be a positive integer. That's what we're seeing here. So just to reiterate what we have seen before, if P denotes the set of all positive integers, then P is itself an inductive set, because first it contains 1, and second it contains x plus 1 whenever it contains x, because it's the set of all positive integers. Since the members of P belong to every inductive set, we refer to P as the smallest inductive set. The set of all positive integers is the smallest inductive set possible. And this property of set P forms the logical basis for proof by induction, which we have seen before. Those are the positive integers, or what we also call the natural numbers, right? As I said, not everyone derives the integers this way. Intuitionists and constructivists certainly do not. They have a different approach to induction itself. So yeah, those are your positive integers. Then when you consider the negation of the positive integers, the negative of each positive integer, then you form a set which is negative integers. The positive integers together with negative integers together with 0 will give you the whole of integers itself. That's the set of integers. If you go on to the nitty-gritties, you will have to figure out how the operations of sum, subtraction, product, how they are satisfactorily an integer or not. But we're not really going into that. If you have time to play around and have fun, you're recommended to figure out those operations yourself and see how far you can go. Those are our positive integers. The rational numbers, they don't really give a lot of context for that. The rational numbers are basically quotients of integers. So you have the possibility of division that we had as one of the theorems. You can get quotients from those, and what the quotients tell you is that if you have a set of those quotients, they are called rational numbers. That's what it is. So the rational numbers, you guys do not know about the modulo operation, but the rational numbers are the modulo of the real numbers by a certain operation. Ignore that, just that rational numbers are a subset after you do a certain kind of operation. The set of rational numbers contain all of the integers as a subset, right? And you have to check, and it should be obvious at this point, that the field axioms and the order axioms are all satisfied by Q. The rational numbers satisfy the axioms and the field axioms and the order axioms of the real numbers. So the rational numbers is called an ordered field. You do not know what a field is. A field is a very specific mathematical structure in algebra and in other field and in other places, but there's a reason why the axioms that we saw first are called field axioms. They define what a field is. I don't know how many of you know about vector spaces, but a field is a vector space with some nicer properties. But whatever it is, it's a field, and the set of rationals satisfy the field axioms and their order, so it's sometimes called the ordered field. All right, and that's for the rationals, and the real numbers that are outside the subset of rationals are called irrational. Right. Then they have another little section on the geometric interpretations on what happens on the real line, right? You all have seen what the real line is. We will see this a bit more rigorously later, but if you look at the figure that they have here, which is you have 0, 1, and you have this line. So, if you go step by step, what you do first is you take 2 points on the line and you represent one with 0 and another with 1. And the ability to do that, the choice of taking 2 points on line, is actually called the scale. That's how you determine a scale. Scale is basically fixing the starting and the ending point. Then if you accept the Euclidean geometry axioms, then each real number corresponds to exactly 1 point on this line, and each point on the line corresponds to exactly 1 real number. So every point on this line is a real number, and as you could imagine, the point is infinitesimally small. So there are so many real numbers between 0 and 1, right? So the line is called a real line or real axis because it is filled with real numbers. Nothing interesting. But what is interesting is that you bring the ordering from the axioms of the real numbers to this. So, it is obvious to us that as we go towards the right, we keep on increasing. Why do we keep on increasing? Because that's how the ordering is. You have the ordering from the axioms such that if you have this A here and you have this B here, then B has to be greater than A, and A has to be less than B. So after 0, things go positive, and as they say, if A is less than B, a point X satisfies the inequalities, which is A is less than X, which is less than B, if and only if X is a point in between A and B. Right? If X is a point in between two points, A and B, then X is less than B and greater than A. Yes, that's much. There's nothing much to say about it. There are certain things where they say how certain approaches to proving theorems is analytic and others are synthetic. The word analytic and synthetic itself comes from different places. Actually, I don't know how much of philosophy you guys read, but if you're familiar with the work of Immanuel Kant, his magnum opus, Critique of Pure Reason, starts with an approach to understanding mathematical statements, and he says geometric statements are synthetic and other statements are analytic. So there he makes the distinction between what is analytic and synthetic. But in general, when we're talking about proofs in mathematics, then a geometric argument is more illuminating or more intuitive or more interesting than a purely analytic proof, because a purely analytic proof, you can do something about geometry in an analytic way without ever drawing a picture. That's the analytic proof. It resists doing anything geometric. And the geometric proof is sometimes called synthetic, where it works from the diagrams and so on. So that's what we do in analysis. As partly our job is to give grounding towards what we do in geometry, rigorous grounding. And thus we are filled with analytic proofs and analytic stuff, which are not as illuminating, but they are the building blocks on which we can do geometry, classic or modern. Okay, I think that's a nice way to end the lecture. Any questions?
was a bit lost when we got to the part about the real numbers. I forgot how they defined them. They started talking about the positive integers right after, so I think I kind of missed that.
Say it again. I could not catch.
When he defines the real numbers, right? It's like,
he doesn't define the real numbers. He takes them to be granted, right? You said
okay.
There's R, something R, which has these things in it, which we call real numbers. But everything about real numbers, you know them through the axioms.
Right. So he doesn't show why they are the way they are. He just says that they are that way.
Yeah, I mean, it's like what we did with sets. Remember when we did axiomatic set theory? I didn't tell you what a set is. I just told you all the axioms that you need to define a set and the operations you need, right? So similarly, you can't. I mean, think about it. Why are they called real numbers? There's no particular reason you can say. I mean, if you even try to find reasons, you can get into tautologies. But the best way to approach is that you assume something is there, which we call real number. We don't know what it is, but then later we rigorously construct the proof of how to define each property and so on. So yeah.
I think I see. Probably just read it over again to make sure to.
Read over what?
The sections.
Yes, you should. You should, yes. Yes, I don't think if I have anything more to remind, because that's the end of the readings for today. Again, you're encouraged to go through the readings yourself afterwards or beforewards, depending upon what fits you. There are course notes as well by Moncrief. Moncrief is an amazing professor and an amazing writer in mathematics. Some of his books are standard textbooks because of how elucidating his writing is. So his notes are also good. You should check them out, and feel free to ask any questions in the chat. Okay, so I will meet you on Wednesday, and we will do something about integers, sigma notation, and some other stuff. We will jump ahead in the book. Actually, we were at 3.7. We will not do 3.8 till 3.10. We will get to 4.1. There's a reason for why we're doing that, and you'll see that when we get to it. But yes, the next readings are from 4.1 to 4.6. But you should not read those things. We will do that in the lecture, but you should read what we did today. And good luck for the P-set if you're still working on it.
Thanks a lot.
Yes. See ya next time.
See you.